Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the next class of CS131 Discrete Structures, where we are discussing the concept of trees in discrete structures. And the very important thing here is that we have already discussed some of the basics of a tree. I've kind of introduced the terms of what a tree is, what a rooted tree is, what a binary tree is, what an emery tree is, etc., etc., and also the different corresponding terminologies of trees in my previous lecture. We had basically talked about the terminologies of trees as well as applications of trees in the previous section, where we talked about Huffman encoding, we talked about binary search trees and decision trees in general. And those were the topics that have already been discussed. In this particular lecture, I'll be talking about tree traversal, the concept of tree traversal. So without further ado, let's go to let's get back to the concept of tree traversal and the slides. So this is what a tree traversal is about. So when you talk about traversing a tree, you know how do you move through a tree? In that, there are some concepts that are very important. So the first thing is the universal address system that we observe. For example, when you're writing up a lecture or a session or a book chapter or something, it's always addressed in this manner that you start with nothing normally in the introduction. And then you have got section 1, section 2, 3, section 4, section 5. In those sections, you may have subsections, subsection 1.1, 1.2, 1.3. And it might be you don't need any subsection, for example, in section 2 or so on. You might need further subsections. So for 3.1, you may have 3.1.1, 3.1.2, 3.1.3, and so on and so forth, multiple subsections and so on. And it can go on till the depth you require. So this is the universal address system. And you can see that this is something that has been used in the a lot in throughout the literature. And this is a commonly used one. So how do you traverse? How do you come up with this? Well, the idea is very simple. You need to use a traversal algorithm for it, an algorithm that actually traverses this tree for you. And there are many different traversal algorithms that are possible. One of them is a pre-order traversal. One of them is what is called the post-order traversal, and one of them is what we call the in-order traversal. And I'll discuss all these three in this particular lecture in quite a lot of detail. So let us suppose that T is an ordered rooted tree with root at R. So let's suppose that you have got a root at R, and this is a ordered rooted tree. So this one is basically the left root, this one is basically the middle root, and this one is the right root, right? So if T consists only of R, then R is the pre-order traversal of T. So if it's only the root, then R itself is the pre-order of a traversal of T. Otherwise, we are going to suppose that we have got T1, T2, and so on till Tn as the subtrees at R from left to right. Remember that this is an ordered rooted tree, so the order matters. So T1, T2, T, and so on till Tn are the subtrees at R from left to right. Then the pre-order traversal begins by visiting R. And whenever you say pre-order traversal, you're first going to visit R. That's the first step, right? Then it continues by traversing T1 in pre-order, right? So then it moves to the leftmost child T1. That's the step 2 mentioned over here. It traverses this one. Then it moves to the next child, traverses this one again in pre-order. So again, now this has become the root. And from the root, if there is any child there, it will move on. If this is just if it's just a leaf, then it is just going to return it. But remember, the first leaf that was, or the first node that was visited was root itself. In pre-order, you first visit the root, then you visit the left subchild, and then the right subchild. So this is the pre-order traversal. In a pre-order traversal, this is what you mean. Get the value of the root first. This is pre-order, right? Then the left subchild, then the right subchild. And this is what we call the pre-order traversal. Okay, so here's an example. So for example, let's suppose this is your tree. In a pre-order traversal, the order would be visit this child first, A, then this child first, this one, because this is the root. So we start with A, B, E, J, K, N, O, P, F, C, D, G, L, M, H, and I. And this is the exact thing that you notice here. A, B, E, J, K, N, O, P, F, C, D, G, L, M, H, and I. And how am I going through this is because I've got a lot of practice for doing it. And that is what you need to do. If you want to master the pre-order traversal, you need to say that whichever node you are working with is your basic node. So this is A, right? And then you need to move to the left subchild and perform in-order traversal for the whole of this subtree. And again, the whole of subtree basically means that I have in my mind that this one will come on later. Both of these children will come on later. But this one B is what I'm going to traverse myself on. And if you know recursion, this heavily implies recursion at its roots. And that is the exact thing that you have already studied in your programming course. So here, now I'll apply for this one and then return back and then do it for C and then for D, and the cycle continues on. And so the answer that I'm getting for my pre-order traversal for this tree is A, B, E, J, K, N, O, P, F, C, D, G, L, M, H, and I. Okay, so here is the algorithm, and if you note the algorithm, this is basically going to recall it. Like I said, this is basically a heuristic, a recursive algorithm. Hence, in a recursion, a recursive function always makes a call back to itself, and that is what is done here. However, notice that the thing here is that for each child C, we first use basically R as a root. We first say that R is the root of the tree, and we list R first. So first thing is to list R. Then we determine the subtree with C at its root. So for each child C in the same order. So we reserve the order, and for each child of C, we first determine the subtree with C as its root, and then we actually pre-order T of C itself, right? So the child, each subtree is then traversed again using the pre-order traversal. And order here is you list the root. That is the first step, right? So yeah, so I'll actually use a marker here. So list R, this is the first step, right? We first use R, and then we just say that determine the subtree in the right order from left to right, and then perform after you determine the subtree, you actually perform pre-order traversal for that subtree continuously. So this is the simple algorithm. On the other hand, just like we saw pre-order traversal, we have another traversal which we call in-order traversal. And in-order traversal is very different from pre-order in the sense that let T be a rooted tree with root R. If T consists only of R, if T is only R, then R is the in-order traversal of R. T otherwise. Suppose that T1, T2, and so Tn are the subtrees at R from left to right. The in-order traversal begins first by traversing T1 in order, then visiting R, and then it visits the next child and so on. So basically an in-order traversal is going to start by visiting this first, right? So it visits this child first, whatever T1, so it visits this side in order form again. So again, this is a recursive call. Then it visits this one, so this is the step 2, and then it visits this one and this one and this one and this one and this one, ultimately reaching this one. So it starts with the left subchild, visits the root, and then the other children. So this is in order, right? And we can actually say for the same tree now, the in-order traversal is going to produce the result as, so it starts from root, but it does not print this one. So it goes to the left child, goes to the left child, goes to the left child. So on reaching J, it's going to print it out. So it prints J, then it prints E, right? Then it prints K, J, E, K. No, sorry. So I'm wrong, a bit wrong here. It first prints J, E, and then it prints the left child of N, K, O, P, right? So J, E, N, K, O, P. Then it goes back, prints B, then F, goes back, prints A, C, and after C, then it goes to the left, prints L, G, M, D, H, and I. So the order here is, if I do it once again, and since this is in order traversal, it starts from A, but it's not going to print it. This is in order traversal, so it first goes to left child, left child, left child performs in order again, goes to left child, performs in order again, goes to the left child of J, which is not possible. So in order here is the result is J. Then it prints E. Then it goes to the left subchild of this one, which is N, right? Then K itself, then O, and then P. And then it goes back, prints B, then F. Then it goes back, prints A, then C, then goes to left subchild of B, left subchild of G, which is L, L, G, M, then D, then H and I as its final solution. So this is again something that is in order, like in the sense that it first needs to go to the leftmost subchild, prints that one, and once it is there, then prints the values, and then the right children, whatever many right children there are. So the procedure is exactly simple. If R is a leaf, then we simply list R. Otherwise, we get the first child of R from left to right. We get the subtree. We perform the in order first. Then we actually list the R, and then for each remaining child C of R, except for the leftmost child L from left to right, we determine its subtree, and then we perform in order on top of it again. And like I said, this is a recursive function. You can see actually two recursive calls that are being made for in order traversal. Okay. Similarly, we can have a post order traversal, and post order traversal is really simple. Basically, let us suppose that you have got let T be an ordered rooted tree with root R. So the first thing that we are going to do is, in this particular traversal, we actually visit the first, in the first step, we visit the left subchild, then the second subchild, then third, fourth, fifth. So in each step, we are actually visiting the children first until it's a leaf. And if it's a leaf, we just return again, like it said, if T consists only of R, then R is the post order traversal of T. Otherwise, you basically move into each subtree, determine each subtree. We first traverse all the subtrees in that order, and finally we return the value R. So that R in post order traversal, R is the last value that needs to be printed. So let's take an example here. On the same tree, if you use a post order traversal, you basically say that first go to this side, right? So first B is going to be visited, then C, then D, and then A. In case of B, again, E is first going to be visited first, then F, and then B. And in case of E, J is going to be visited first, then K, and so on. So for K, of course, K will not be visited. Instead, N, O, P, and K will be visited. So in this case, the order is going to be J, N, O, P, K, E, F, B, C, then L, M, G, H, I, D, and finally A, and we are done. So this is the post order traversal of the same tree. And the example here is very simple. Notice that the only difference here is that there we were listing R before this for loop. Here, in the case of pre-order, we were listing R before this for loop. In this case, the only difference is that we actually list R after this for loop. And notice that this is outside the for loop, hence this has nothing to do with this. Actually traverse each of the subchild first, and if there's no child left, then you automatically list R and return. That's it. So this is the post-order traversal of that. So now talking about some of the applications of tree traversals, well, we can represent complicated expressions such as compound propositions, combinations of sets, and arithmetic expressions using ordered rooted trees. For instance, consider the representation of an arithmetic expression involving the operators plus for addition, minus for subtraction, multiply, asterisk for multiplication, backslash for division, and an upwards arrow for exponentiation. We'll use parentheses to indicate the order of the operations. An ordered rooted tree can be used to represent such expressions where the internal vertices represent operations and the leaves will represent the variables or the numbers, and each operation operates on its left and right subtrees in that particular order. So for example, what is the ordered rooted tree that represents the expression x plus y raised to power 2 plus x minus 4 divided by 3? In this case, we know that x plus y is represented like this. Raised to power 2 can then be represented by using this and in this manner. And this basically shows that if you want to evaluate it, it is x plus y raised to power 2. Then the second part is x minus 4. And then after x minus 4, you have to divide it by 3. So then divide by 3 comes at top of it. And if you combine these two together by using another factor, which is basically plus, so you can add a plus on top of it to make it a rooted ordered tree like this. So this represents x plus y, then you raise it to power 2, and then you add to it x minus 4 divided by 3, and that whatever comes out, you need to add it to this particular portion. So that is the thing. So if you, where does the infix form of expression comes important or handy? Well, an in-order traversal or infix, an in-order traversal of the binary tree represents an expression producing the original expression with the elements and operations in the same order as the originally occurred, except for maybe unary operations, which instead immediately follow their operands. Yeah, so anything that is unary will follow their operand. However, otherwise, for instance, the in-order traversal of the binary tree in figure, which represents the expressions x plus y divided by x plus 3, x plus y divided by x plus 3, and x plus y divided by x plus 3, all lead to the infix expression x plus y divided by x plus 3. To make such expressions unambiguous, it is necessary to include parentheses in the in-order traversal whenever we encounter an operation, and the fully parenthesized expression obtained in this way is said to be an infix form. For example, in this one, we can say that these are the three operations, three binary trees, and each of them is basically going to lead us to, in the infix operation, it is going to lead us to x plus y divided by x plus 3. And similarly, this one is x plus y divided by x plus 3, and x plus y divided by x plus 3, and so on. So that's the thing here. And these are three different trees that are going, if you don't include brackets, if you don't do it like this, then they all lead to x plus y divided by x plus 3 in general. So if we take the prefix form, well, we obtain the prefix form of an expression when we traverse its rooted tree in pre-order. That is what we call prefix form. The infix form is obtained by basically using the in-order traversal, right? So that is where in-order becomes handy. If you use the pre-order or prefix form of an expression, we can obtain that by traversing the tree in pre-order form. Expressions written in prefix form are said to be in Polish notation, and an expression in prefix notation where each operation has a specified number of operands is unambiguous. There's no ambiguity here. In the in-order traversal or infix form of expression, the problem is that the result may be the result may cause ambiguity, and you will have to use brackets. Without brackets, this is an ambiguous situation. For example, these three are exactly equivalent. However, in a prefix form, it will always result in an unambiguous situation. So in a prefix form, no parentheses are needed at all. And again, you can practice it using here. So evaluate the prefix form of expression this. So for example, let's suppose that we have got an expression which is in prefix form and we want to evaluate it. The idea here is simple. We start with this one. So we basically 2 raised to power 3 is 8. Then we divide 8 by 4, which is 2. Then for 5 and 2, we need to multiply them, right? So sorry, for 2 and 3, we need to multiply them. So that's the next portion. 2 into 3 is 6. Then 6 minus 5 is the next step, right? And finally, you have got 6 minus 5 is 1. So 1 plus 2 is going to give you 3. The value of this expression is going to be 3. Notice that this is what we do. So wherever we have got to an operator, we use it for the next two possible numbers. So we divide here by 2 and 3, and we start from the rightmost operation, rightmost alphabets. 2 raised to power 3 is 8. 8 divided by 4 is 2. So this is, after this particular, we get 2. And now we need to move on to this side. Since this is operator, we apply it for the two nearest ones. So this gives us this one. And then we can basically use this and so on and so forth for the whole of the portion. Okay, So, and finally, we can actually evaluate the result to 3. This is how prefix evaluation can be noted. Similarly, we can obtain the postfix form of an expression by traversing its binary tree in post order. Expressions written in postfix form are also said to be in reverse Polish notation, and expressions in reverse Polish notation are also unambiguous, so parentheses are again not needed for this one. And the reverse Polish notations was extensively used in electronic calculators in the 1970s and 80s. However, it has not been used since then for electronic calculators. So for example, if you want to evaluate this postfix form, again, the thing that you need to do is start from the left, but in this case, find the one that are with an operator. So 2 into 3 is 6, right? So 2 multiplied by 3 is 6. Then the next one is 7, 6 minus. So you basically subtract 6 from 7 and you get 1. Now again, 1 raised to power 4 is the next thing. And this gives you 1. So now you need to get to this divide. So 9 divided by 3 gives you 3. And 1 plus 3 gives you 4. The value of expression is 4. And that's how you evaluate a postfix form. So let's take another example. Find the ordered rooted tree representing the compound propositions not of P and Q by implies not P or not Q. Then use this rooted form to find the prefix, postfix, and infix forms of this expression. So of course, P and Q can be represented like this, right? So this first we have to come up with the ordered rooted tree representation. P and Q, not P and not Q. You can represent that, right? So P and Q, not of P and Q can be represented like this. And the other part, or, so an or for these can be grouped together using this statement. And then you can use the by implies on top of this to represent it in the ordered rooted tree, rooted at the by implication. So the prefix, the postfix, and the infix forms of this expression are found by traversing this tree in pre-order, post-order, and in order, including parentheses respectively. So of course, for in order, you need to have parentheses involved. And these traversals give. So remember, if you use braces, they'll give back the exact expression. The in-order traversals of this tree, if you use braces as well, will give back this particular expression again, if you have got the correct tree. However, for the other ones, well, not necessarily, but again, if you are reading them in the pre-order or in the post-order, then you are able to solve them correctly as well. If you can evaluate them, they'll come back to the same value. And that is mentioned over here. I won't go through them here, but they're really simple and you should be able to go through them. So for example, in the pre-order one, you always go to the left, right? Left child, this P and Q, right? Followed by basically, so if I was to evaluate this in pre-order, I would have basically gone by it by P and Q, not of P and Q, by implies, and then evaluate this side, and so on. So that's the pre-order or prefix notation, and I can use it, the pre-order traversal, to traverse it correctly or evaluate it. For postfix, again, I can do the same thing and so on. So that's, I think, yeah. So again, where are these notations used? Because prefix and postfix expressions are unambiguous, and because they can be evaluated easily without scanning back and forth, they are used extensively in computer science, prefix and the postfix ones. Note that. However, they are hard for a human to understand directly, and a human actually understands the infix expression much better. So the expressions, the prefix and postfix expressions, are especially useful in the construction of compilers. So when you study the course of compiler construction, in particular, you're not going to study that, but maybe the computer science students are going to do that. For them, the prefix notation and the postfix notation are very interesting and important. However, for humans, maybe the prefix notation is much easier to understand and much easier to represent, although you might need to use brackets in them, and with brackets, things are a bit different. But for humans, those are the easier ones to use. That is why you'll see the use of all of these three notations in various different programs. So with that, section 11.3 comes to an end. We have basically discussed about tree traversals, and we have discussed about notations and in order, pre-order, and post-order traversals, and how they can be used to get the prefix notation, postfix notation, and the in order and the infix notation for your tree. And by representing tree in that order, we can actually use them on various programs and various stuff. You might need to do a bit of practice before you are comfortable with each of these notations and why they are working. In particular, the concept of recursion here is scintillating and very interesting, and that is something that you have studied in CS103, your computer programming course. And I'm really hopeful that you have learned something about tree traversals in this particular section. We talked about applications of trees and introduction to trees in the first two sections, and the last section, the current section that we studied just now, is about the tree traversals. In the next section, we will then be talking about spanning trees and how you are going to traverse spanning trees. So with that, I'd like to thank you all for listening to this lecture, and I hope you learned something about tree traversals in this lecture. See you in the next lecture. Take care, and Allah Hafiz.